So we are going to talk about rational and irrational numbers. So last year in seventh grade, you should have had a discussion about really what rational numbers look like and identifying if it's rational or not. So really, we're just throwing in an extra word here of irrational number, which is not rational. So hopefully we kind of remember this from last year. A rational number is technically, the technical definition is a number that can be written as a ratio of two integers. Okay, but really what we mostly think about is, can we write it as a fraction? So rational numbers are numbers that can be written as a fraction. Okay, and irrational is just the opposite of rational. So irrational can't be written as a fraction. Okay, so we're going to list the types of numbers or maybe some examples that we're dealing with when we're looking at our rational versus irrational numbers. So we're going to start with the most basic number. So rational numbers are numbers like, so I'm going to say whole numbers. We'll do whole numbers, which is our 0, 1, 2. Those are rational. And the reason is you can take, the number 3 and stick it over 1, and now it looks like a fraction. So that's a rational number. Okay. Integers. So the negatives are also rational, because same thing, if you have -4, I can take -4 and put it over 1 and make it look like a fraction. So our nice whole numbers, our nice integers, those are all rational. Obviously, if we're talking about things that can be written as fractions are rational. Also, mixed numbers. Okay, because something like 2.5, we'll keep it easy. 2.5 is a mixed number. Okay, that can be written as a ratio of two integers, can be written as a fraction by just changing it into an improper fraction. Okay, so 5/2. So mixed numbers are rational. And then two types of decimals. Okay, so we have terminating decimals, which is essentially decimals that end, they stop. So for example, 0.2, -3.15. I tried to mix it up and show you it doesn't matter if that decimal is positive or negative. It could be a 0 as a whole number, another number like 3 as that whole number in front. Just terminating decimals, decimals that stop, those are rational. Okay. And then also repeating decimals. And keep in mind, there's two different things that can happen with repeating. We could have something where just, it could just be the one digit repeating. It could be something like there's a couple numbers and then a digit at the end repeating. It could be a mixture of a couple things all repeating. So it doesn't matter where the repeating happens, but if it's a repeating decimal, okay, that can be written as a fraction. And we're going to be talking about how to actually turn it into a fraction in a different video. But just for now, know that terminating decimals and repeating decimals are rational. Okay, so that's a lot of stuff that is rational. Okay, there isn't a whole lot of scenarios we're going to deal with where it's irrational. So I almost think it's just easier to look for those examples that are irrational, and then really everything else is rational. But it's up to you how you want to think it through. So irrational, remember, can't be written as a fraction. The most famous irrational number, I believe, is pi. Okay, I'm sure you guys have talked about pi in the past. Okay, it is a decimal that is ugly and nasty, and it never stops. It goes on forever. There's no repeating. That is probably the most famous irrational number. What we're going to be dealing with more may look something like, 6.2579. I'm just making up a bunch of numbers. 3, ... So the ... is showing that it's going on forever. It doesn't stop. But at the same point, there's no repeating going on. I could have also, if I go back to my other side, my repeating decimals, I technically could have written that first one like that. Okay. And I'm showing with the ... it's going on forever. But I can also see that the 2 is clearly just repeating. So we don't usually write our repeating decimals like that. We like to use that bar notation. That's that little bar we put on top of the repeating part. Okay, but we could technically write it out. So now on the other side of things, if I have that dot, 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 but there's no repetition going on, that's just showing it's an irrational number. Okay, there's going to be lots of numbers after that I don't even know what they are. Okay, because it's impossible to write them all out. Another thing that is going to be irrational, something like this. I'm going to do 1, 2, 1, 2, 2, 1, 2, 2, because for some reason this one always gets you guys, because you're like, oh, there's a pattern. It's rational, but it's not about a pattern. Okay, I can see that each time I extend it, I add an extra 2 in there, but nothing repeats. It's not like it's 1, 2 repeating, because that would look like 0.12, 1, 2, 1, 2, 1, 2, etc. So there's nothing repeating here. So even though there's a pattern, this is irrational. Okay, and then the last thing we're going to talk about is something like the square root of 5 or the cube root of 30. Okay, we talked about square roots and cube roots. And the reason that these are irrational is because this number on the inside of my square root is not a perfect square. Okay, no nice number, I should say, no nice number times itself gives you 5. There is an answer, but guess what? It's an ugly decimal. Hence, it's irrational. Okay, so no nice number times itself gives you 5. It's not a perfect square. So the square root of 5 would be an irrational number. Same thing. Cube root of 30, no nice number, times itself again gives you 30. So when we have a cube root of something that's not a perfect cube, that will also be irrational. Okay, so you just have to identify, is that number on the inside a perfect square or a perfect cube? If you can do it. So like if I gave you root 16, guess what? The square root of 16 is 4, and that's rational. If I give you the cube root of 8, which is 2, that's rational. So really it comes down to knowing your perfect squares. Remember, I'm not going to make you go super duper high, but knowing your perfect squares and a couple perfect cubes and being able to identify if it would be a nice number or not if you did the square root of it. So that's pretty much it. That's rational versus irrational. And our practice for this is just going to be me giving you a bunch of numbers and you telling me if it's rational or not.